So let's start our talk about phase change diagrams, different phases of matter. And out here I have really the three major phases of matter. And you guys have been learning this since grade school. And you should know these by now. Solid, liquid, gas. Remember, solids are packed in very tightly together. They have a definite volume, definite shape, and they really don't have a lot of energy. The atoms are moving, but not a lot. So it's called a vibration, so like a lot of movement. The next one is liquids. And remember, they don't have a definite shape. A liquid will fill any container that it's put into, but it does have a definite volume. And they're a little bit closer together, so that they're not, the intermolecular forces are going to hold them all together. And then our last ones are gases. And gases are, they'll fill up any container. They have no definite shape, no definite volume, but they have high energy. And these are the three major phases. And if you remember, like freezing or evaporating, stuff like that will change you to different phases. But what I really want to look at right now is a phase change diagram. And it's just a graph. It sounds fancy, but it's not. Let's look at it. So this is called a phase change diagram. So if I tell you to pull up a phase change diagram, this is what I'm talking about. And if you look here at these vertical lines right here, I'm going to try to highlight them. These are the actual phases right here. And so gas, liquid, solid. So gas, liquid, solid. And if we look at our y-axis, we have temperature right here. So as the temperature increases, it'll change what phase we're in. But it also goes by our heat energy, how much energy each of these has. Remember we said that gas has a high amount of energy, liquids have a medium amount, and solids have the less amount of energy. These flat lines right here that are leveled out, this is where temperature stays the same. Temperature's staying the same right here before it actually jumps to the next phase. So if I have some water and I began to melt it, you can sit there and measure the temperature of our ice, and then it'll stay the same, and then it'll jump down to a liquid. We did a lab not too long ago where we made milk, or not milk, we used milk to make glue, and a lot of people's temperature began to level out after a while, and that's normal, and it's because of this. It has to do with the amount of heat energy being absorbed. There's really two key concepts I really want to pull from this besides knowing how to read this diagram, and it is endothermic and exothermic reactions. And I'll write them right here in blue. Endothermic, let's talk about that one first. An endothermic reaction is going to absorb energy. Absorb energy. Okay? So it's going to pull in more energy. As things go across this way, it's going to be an endothermic reaction. So as little water, as it boils and turns to evaporation, it's an endothermic reaction. And then the opposite of that is an exothermic reaction. Exothermic, and this is going to release energy, okay? So as water begins to freeze, it gets colder, but it's actually releasing energy. I know that seems a little off. An explosion would be an exothermic reaction. It's pushing out that heat into the environment, or if you burn a log, as the log is burning, it is releasing heat, and it's releasing energy in the form of heat and light. So endothermic is going to absorb energy, exothermic is going to release energy. And when we look at these phase change diagrams, temperature will be on our y-axis, and heat energy is on our x-axis, and it's going to be these vertical lines that are actually going to be the phases. And then as the change, it's going to stay the same temperature, but it requires more heat energy.